Yes, thank you. So once again, I'd like to thank the organizers for this opportunity. And the title of my talk is on some recent work by myself and my advisor and some collaborators relating to best packings and best coverings. So the statement of the problem can be introduced as follows. Given a compact set, what are the maximal number of disks which can be packed into the set with no overlap? Or similarly, there's the dual problem of covering, which asks for what is the minimal number of disks needed to cover that given compact set. Now, these questions have some interesting applications. For example, if you have a gas that's fitting in a container or some large region, how will the gas expand to fit the container? Or in the case of covering, you might think about how do you distribute an important resource over a large area with irregular shape to make sure that all regions in the area are equally served. So I'd like to move on to this first visual example to sort of help illustrate the point. So I have two squares, both presented here, where I have a configuration of 4 points covering the square. Now on the left, I've placed the 4 points in sort of a well position so that the 4 disks, all of equal size, sort of best cover this entire square. And you can probably notice that I've attempted to minimize the overlap as much as possible, which sort of helps in reducing the size of the disk. On the right, what I've done is I've taken those 4 points and sort of nudged them closer to the center of the square. And that intentionally sort of messes up the covering slightly by doing the following. So by moving the points that were placed in these specific points on the square intentionally towards the center, I've moved the configuration further from the corners of the square. So those corners, which were sort of the far away points of the square, are now further away from the covering, which necessitates that I must increase the size of the disks in order to achieve that same covering. So on the left, we can have what we could say is maybe a well covering of the square with 4 points. And on the right, we have a slightly less well covering, or maybe just a poorly covered square of 4 points. So this sort of illustrates the idea that the set is sort of fixed, and we want to think about how does changing the placement of the configuration of points affect our covering of the square. So now to get into sort of the formalities of our definition. So let's start with best packing. So throughout the rest of this slides, RP will be our ambient space. So this is the ambient space where everything is living inside of. My configuration will be omega n, which is n points collected in my ambient space. Then we define the following to be the minimum distance of any pairwise points. So you just take a look at any 2 points taken from my configuration and find the minimum distance between 2 pairs. And it's a minor point, but for packing, we want these to be distinct points, but that's not really too hard of a restriction to put on ourselves. So we just take configuration, look at all pairwise distances, and find the minimum such pairwise distance. And that will be delta of our omega n. Now, given our set A, which we want to have infinitely many points, so not a finite set, we want it to be compact, we can define the best packing distance on it as follows. So take that delta of omega n, so pairwise distance, and now consider all configurations omega n over your set A. So now I'm thinking about how does changing the configuration affect the distance? And I want to fix it so that I'm only considering omega n's that have a fixed number of points. So to go back to the previous case, I did not change the number of points in the configuration. I kept it with 4 and just looked at how does changing the placement of the configuration change the covering, or in this case, changing the packing distance. And then we take the supremum over all of those configurations. So down below, I have 2 examples of packing on the set, the unit interval 0, 1. So here, my number of points in my configurations is 5 in both cases. And over here on the left, we have the optimal packing, where I put 2 points at the endpoints and then divide up the rest of the interior of the interval into 4 equally spaced subintervals, and then place my points at the subdivision of each of those subintervals. So this gives us a good separation between each point of the configuration and its nearest neighbors. And then over here on the right, we can see that we have something that's poorly separated where I've got several points clustered together and lots of free space over here on the left and right where I could be pushing my configuration out to better serve this clustering. Moving on to covering, we have sort of, because it's a dual problem, there's a couple things that swap around, but essentially there's a similar concept that's being underplayed here. So again, we'll take an infinite compact set and define the best, and I'll explain constrained here, covering distance of endpoints of a configuration on A as follows. Take your configuration omega n and look at all points y in your set A. And you want to look at those points y, which are maybe pretty far away from your configuration omega n. So these will be the points that sort of define your covering distance, because for a point that's really far away. Oh, yes.
Packing means you can put balls in a box or you cover the box.
Packing is putting the balls in the box.
Okay.
And then covering is the opposite question of I'm trying to contain a box with a union of balls.
I see. Okay.
Yeah, so that will require us to do some swapping of the arguments. So before with best packing, it was a minimum of distances, and then we took a supremum. So here with covering, because of the dual nature of it, it's going to be a maximum of the points y, which are far away from your covering. And then we want to minimize that covering distance over all configurations. So there's a similar idea working, but there's a slight difference in the dual nature of it, where we have to swap the argument of the sort of taking the minimum of something and then taking a supremum. And for covering, we take a maximum and then a minimum. So, and this has some implications for the calculations later on, but it mostly comes down to changing inequalities to their opposite. So this is a constrained covering because we want the constraints to be our covering points to be contained inside the set A. And then if we also consider the set of points omega n star no longer restricted to the set A, but instead the ambient space, this is the unconstrained covering. And we just denote this with eta n star. So the star indicates unconstrained. And we just replace omega n with omega n star in our definition. And then the minimum occurs over all configurations taken over your ambient space. So for the unconstrained, we could be allowed to take the center of the ball to be outside of the set A and still cover portions of A. Now, best packing and best covering are specific cases of a more general definition, which is that of minimal energy and polarization. So minimal energy is presented as given a lower semi-continuous kernel from A cross A to infinity or minus infinity up to infinity inclusive, and then given a configuration omega n, similar to how we've previously defined, its K energy is given as we take the pairwise sum over all kernels calculated from any two distinct points, xi and xj, and then whatever minimum energy is obtained for a given configuration omega n, we define that to be the minimal K energy. So you could think of this as, for a given example of a kernel, take the inverse of distances. So if 2 points are really close, that's going to contribute a very large amount to the kernel and thus to the overall energy. But if 2 points are really far away, then their inverse of distance will be fairly small. So that's not going to contribute too much to the energy. So if you think of, if you have two magnets of the same polarity and you push them together, they want to repel. So it wants to enact a large energy on you. Whereas if you hold them far apart, they're not really acting on each other as strongly. So this sort of picks up the idea of a best packing with a kernel. And if you make that kernel very strongly repulsive, then you would get a best packing. The similar idea to covering is encapsulated by the maximal polarization, which takes the following. So again, we have a lower semi-continuous kernel, where here we're taking the kernel of points xi in our configuration calculated from some selected point Y in the set A. So this is similarly formulated as how we did for a covering, where you have your configuration points of your covering, omega n, and then you're considering a point Y, which is maybe very far away from your covering. So in the case of the square, we saw that those points Y that determined the covering radius were the corners of the square because they were far away from sort of the interior parts. Then if we consider the minimum of this summation, we get this pk of A of omega n. Then the nth K polarization, or sometimes called the Chebyshev constant of A, is defined as the supremum of pk of A of omega n, where that was the infimum. So again, like we saw with the covering, we take an infimum and then we take a supremum over this summation. So that sort of matches the order of the arguments of these infimums, supremums, and maxes and mins. So polarization and energy are these extensions of these simpler cases of packings and coverings. Now, why is this important? Well, there are some recent results on polarization that sort of tried to characterize the asymptotics of polarization on given sets, but they've pushed those results as far as they can before it's gotten really difficult to get new results in polarization. So what we're attempting to do is take an alternative approach and take known results for polarization and apply those to the specific case of coverings and packings, which are a little bit easier to work with. Then hopefully we can discover some new results for covering and packings, which will then make it easier to sort of gain new results in polarization. So we're hoping to gain some insight on what happens with the coverings and packings before hopefully pulling it back to the case of polarization. And in this, we were able to extract a few things which does have some implications on polarization. And so I wanted to talk about those main results that we obtained for coverings and packings and a little bit on their implications. All right, so the main theorem that sort of has implications that's featured in a recent paper that we have on arXiv is the following, which is an exact extension or replication of what has already known about polarization. So this was a fairly simple theorem that we were able to extract just by considering the simpler case, which is given a compact set A inside of Rp, and integers d and p satisfying the following relation: 1 less or equal d less than or equal p, where p is at least 2. So that we do require that the ambient space needs to at least be R2 or some higher Rp, where d is our Hausdorff dimension of our set A. So we want our Hausdorff measure of A to be positive. Then, if the limit of the unconstrained covering, and then we have to account for this growth factor of the covering. So as we asymptotically increase the number of points in the covering radius will shrink, but that shrinking will be of the order n to the 1 over d. So it'll be shrinking at a rate of n to the 1 over d. So dividing by n to the 1 over d. So if we multiply by an additional factor of n to the 1 over d, that sort of accounts for the growth decay of that covering radius. And if that approaches some finite limit, then this theorem guarantees that not only does the limit for the unconstrained case exist, but the limit for the constrained case also exists. And in fact, that these covering radiuses will agree, or that these limits will agree. So what this essentially says is that as you asymptotically increase the number of points in a best covering, those covering radii will shrink, but also that the best covering in the unconstrained case will be very similar or essentially similar to the constrained case. Now, this is, as I said, just an extraction of something that we saw previously for polarization. And the way that we derived this was a little bit easier than the case for polarization because of the fact that covering is slightly simpler. We were able to make some essentially shortcuts through getting through this proof. And this main theorem hinges upon a couple of things, just being that covering is a little bit more flexible, where if you move a point and its covering sort of has a lot of overlap with neighbor points, you can sort of move that point around and still have that same degree of flexibility and not affect your covering at all. So as I said, this result and its contrapositive has some additional results worth discussing, but because of the limited time, I just wanted to look at the main application that we derived and was the focus of our paper. So I said previously that the growth order of packing and covering features the same growth order, and that's presented here. And this is one of the main things that we're able to use, is the fact that because packing, covering, and unconstrained covering all have this similar growth order, we expect similar behavior with these limits that are mostly the same. And so since proving exact answers is in general hard, that's why we're working a lot with the asymptotics to sort of get an idea of what's sort of the asymptotic behavior as we increase the number of points. So we're taking D to be the Hausdorff dimension of our set A. Then we get this growth decay of our set A for n points. And we can see this with the following sort of simple example. So if A is the interval from 0 to L, so it has length L, then if I wanted to cover it by exactly 5 disks, then I'd place them like this so that they are only touching at these boundary points, so that it exactly covers L as best as possible, so that the radius of each disk will just be L over 2 times the number of balls. So if I have 5 balls, it'll be L over 10, and that's given here, L over 2n. So this is decaying at the rate of n to the 1 over d, because in this case, our Hausdorff dimension is 1. So it's sort of easy to see this in the case of d equal to 1, but going into higher dimensions, it's a little bit not so trivial to see that this is the case, but this is indeed the growth decay for a compact set in of dimension d sitting in your ambient space RP. And we make use of this fact throughout. So it's just important to sort of point out that this is not super obvious in higher dimensions, but it is true. And if you sort of work through dimensions 1 and 2, you can sort of hopefully believe it. Now, one of the main theorems that we've been looking at and attempting to expand is the Poppy-C-Bagel theorem. And I've stated it here in terms of packing, which essentially encompasses the following. Given some smoothness assumptions on your set A, we can guarantee the existence of asymptotics for best packing and best covering. And the general case was also shown already, which was for minimal energy and maximal polarization. So presented as following: let A be a smooth D manifold that's been embedded in RP, and let HD denote the D-dimensional Hausdorff measure. So in our case, it'll just be the surface measure of A. Then, so we have this similar limit as presented before, where we take the best packing distance and then account for the growth decay of the best packing, which is again going to be the same as the growth decay for best covering and for best unconstrained covering. Then this limit exists and it equals this, where CD is a constant depending only on D. And then we have our surface measure, and then we just have to account for the dimension of the set. So we regulate it to 1 over D. And we can see this with the picture on the following, why it's called the Poppy-C-Bagel theorem. So here I have a torus, which looks like a bagel, and I have my poppy seeds, which are the configuration points, and I've equally spread them all across the surface of the bagel. So this sort of guarantees in layman's terms that your perfect bagel exists with poppy seeds, where every bite of equal size will have approximately the same amount of poppy seeds. And then continuing from before, the constant CD is just the largest sphere packing density in RD divided by the unit ball in RD, and then regulated to the 1 over D power. Now, there's a second part to the Poppy-C-Bagel theorem, which I didn't write down for the sake of time, but it essentially just guarantees that the packing configuration is uniformly distributed for large N. So with enough poppy seeds, we can guarantee that we do get an equal spread, and that ignores the curvature of the torus. So out here where the curvature is positive, you still have roughly the same packing distance as on the interior where the curvature is negative. And this happens asymptotically for packing. And in the case of polarization, you do have to sort of take into account that you need the repulsive kernels to actually be strong enough. So for polarization in energy, if that kernel is not strongly enough repulsive, you end up getting a clustering along the positive curvature boundary and not the negative curvature, or the spacing on the negative curvature is a little bit larger than on the positive. But for packing and covering, it's uniform throughout. Okay. Now, a previous result that was shown by Kolmogorov and Tikhomirov is that the analog of the Poppy-C-Bagel theorem is true for covering, but they only showed it for Jordan measurable sets and only in the unconstrained case for full dimension, with no discussion about the distribution of points. So here we've sort of tried to replicate what their theorem would say if we sort of tried to match the notation that we already presented. So take a compact set with measure zero boundary, and then we have a constant that's defined similarly to the packing constant before, where in this case, it's the covering constant of the unit cube in RP with respect to the covering in, or the number of points in, and then we have to regulate it up to some size. Then if that coefficient or that constant is positive, then we get that this limit equals a similar result to what we saw previously, where we've replaced the Hausdorff measure with the Lebesgue measure of A. Now, we took this previously known result, and then by theorem one that I showed earlier, this result hinged upon the unconstrained case. But what we showed in theorem one is that under some certain assumptions, the unconstrained covering and the constrained covering can be made to be equal under the asymptotic limit. And oops, I think this lowercase n should have been an uppercase n in this limit argument. So this is the limit as capital N is going to infinity. So it's still the asymptotics of the number of points of the configuration. So here is our corollary, which was one of our main results, which was that given that we know from theorem one, the existence of the unconstrained covering asymptotics implies and guarantees the existence of the constrained covering asymptotics, and that those limits agree, we just get for free this theorem for the Poppy-C-Bagel theorem for the case of the constrained covering. So here, this is just automatically for free, given a set A and RP as a compact set with zero boundary. Then we get that this limit also exists and is going to be equal to the first, which is why we have this same equality on the right. Now, the case of the Poppy-C-Bagel theorem for packing was shown under very mild smoothness assumptions, which was on sets that have the image of a compact set under a Lipschitz map. And I didn't have time to fully go into that case for covering, but we were able to extend this result to similar smoothness assumptions. So not only were we able to take this for a compact set of measure zero boundary, we were in fact able to drop this condition about the boundary being measure zero. And so that was sort of one of our main results from the recent paper. And that concludes my talk. I do have the sources that we were working out of, so a lot of this. And if I can point out, I think one of the major papers we were working off of was from Hardin and Saff. So their work on polarization was sort of the main foundational point that we were working off of. So thank you for your time.